What we're going to do is today is going to talk about the processes that take place in the proximal tubule. We'll have recordings that go over each area of the nephron tubule, and this one specifically is going to address the events, major events that take place in the proximal tubule. In the proximal tubule, you'll notice it says proximal convoluted tubule. Well, there's a subtle distinction. Is the proximal convoluted tubule is where you see it all convoluted, all kind of coiled up. Proximal tubule is where you have it just straight. But similar things will take place in both, so I really don't, it doesn't matter to me that you know the difference between them. But what is it so special about the proximal tubule? Well, the majority of reabsorption in the nephron tubule takes place here. If you notice, if you look at the histology of it, you have these cuboidal cells, simple cuboidal cells, and they have this brush border, which are microvilli, that increases the surface area for absorption or reabsorption. The majority of reabsorption of ions, especially sodium, takes place in the proximal tubule. All organic molecules like glucose and fructose, amino acids, all the nutrients, and we'll call them nutrients, they're only reabsorbed in the proximal tubule. We have secretion of drugs. We have secretion of hydrogen ions that takes place there in the proximal tubule. We have a large amount of reabsorption of water that takes place there. And so what is it that allows us to do that? Well, we have that brush border. They have a lot of mitochondria, and that mitochondria need energy because there's a lot of primary and secondary active transport that takes place in the proximal tubule. So they have a lot of that. They have a lot of transport proteins, a lot of channels, and these other transport proteins that make it easier to reabsorb these substances. So kind of before we kind of go over different things that take place here, is I want to talk about different routes for reabsorption. Is you have what we call a transcellular route, so it goes literally means across the cell. So substances will move through membrane transporters or channels. And here at the luminal membrane, you see you have a transport protein. But we're going to have some over here on the basolateral membrane. Those would be things that are large or polar. They need to go through this route. If you're an ion or water, you can go through this paracellular route. So you can squeeze in between the cells, and how much does determine by how tight these junctions are. And if it's very, very tight, nothing's going to get through. But you can squeeze through some areas right here through this paracellular route. So let's kind of look at reabsorption in the proximal tubule. So I had mentioned that only the nutrients, or should I say nutrients, are only reabsorbed in the proximal tubule. They have these co-transport proteins, or these symporters, that they are transported along with sodium. And you see these co-transporters or symporters in the apical membrane, and they're specific. You have ones for sodium and glucose, some sodium and a particular amino acid. So they permit the various organic molecule to come in with sodium, and over here on the basolateral membrane we have then a transporter that allows it eventually to go into the bloodstream. But a big thing to notice is right here is in the basolateral membrane you have a lot of the sodium-potassium pump, the sodium-potassium ATPase. What that does, remember, is a primary active transporter, is what it's doing is creating a favorable gradient for sodium to want to enter the cell. And so you see the sodium is going to be pumped out here, and so sodium is going to want to drive, and it's keeping the concentration in here low, so it's driving that movement of sodium. And since we have this co-transporter that can bring in something else like glucose, the other substance is going to come along with it. So technically what you're seeing over here is an example of secondary active transport. So the expenditure of energy was over here, But this would not happen without this happening. So that's why you need a lot of mitochondria in the proximal tubule, because that sodium-potassium pump activity is making a favorable gradient for sodium to want to go into the cell, and that drives the movement of a large number of substances. And it's not just organic substances, things like phosphate, lactate, a number of different things are going to come in with sodium. Now you also have various ion channels. So a lot of ions will be reabsorbed in there. Water moves passively. So, and actually tends to go this paracellular route. But we do have some ions that will also go through that paracellular route, and that'll kind of be drawn along with the water. Water, remember, only can move passively. It moves by the process of osmosis. It goes from its high concentration to low concentration, and it follows the solutes. So as you're reabsorbing all these solutes over here, water is driven. And so the concentration of the tubular fluid, I should say, over here, will be the same as what you see over here. So it's going to be isoosmotic to the plasma. And what drives all this movement of water is that reabsorption of the ions and the nutrients that take place. Another thing that takes place in that proximal tubule is, and actually you see here's showing it a little bit better, is that sodium-potassium pump. So you see again, sodium and organic solutes, phosphate, those things are going to be driven in because of that, and you see water sneaking in here. A big thing actually happens in the late distal tubule is more of the chloride is actually transported passively in the late distal tubule, and it comes in with that water. Now the other thing that you'll notice here is we have secretion of hydrogen ions. So in that luminal membrane you have a sodium hydrogen exchange protein. Well, the secretion of hydrogen ions is actually necessary to be able to reabsorb bicarbonate. So I want to show you kind of what's involved here. And so again, you got that sodium-potassium pump over here on in the basolateral membrane. That's creating that favorable gradient for sodium to come in. And in exchange, so this is actually an antiporter that you're seeing, that exchange protein. The sodium hydrogen exchanger is the sodium coming in is exchanged for hydrogen ion going out. But what that's needed for is actually for the reabsorption of bicarb. Now we do need to keep the bicarb because bicarb is a very good buffer, prevent our pH from getting too low. So it's a very good buffer, so I want to reabsorb it. Now we will talk about, when we talk about acid-base balance, there's some instances, yeah, I don't want it, so we will get rid of it. But here, if I want to reabsorb the bicarb actually combines with the hydrogen ion and forms carbonic acid. So H2CO3 is carbonic acid. Now this is taking place in that brush border. So we have an enzyme called carbonic anhydrase in that brush border. That when the carbonic acid, I meant to say carbonic acid, is right there. And carbonic anhydrase catalyzes that reaction. Well, the carbonic acid will disassociate into water and carbon dioxide. And what happens, and this here is in that cell in the proximal tubule, is that will then combine back together, which seems kind of weird, is using carbonic anhydrase, you form carbonic acid inside the cell, and then that dissociates into bicarbonate, which then I'm going to co-transport it on the basolateral membrane along with sodium, and I'll be able to reabsorb it. The hydrogen ion that resulted from the dissociation of carbonic acid was then just secreted. And so you really don't have any net secretion of hydrogen ions, because every one hydrogen ion that's secreted, you can reabsorb one bicarb. So the secretion of hydrogen ions in the proximal tubule is actually necessary to reabsorb a bicarbonate. Okay, seems kind of like long and drawn out, but just the way it works. Okay. So we have secretion of hydrogen ions. We do have secretion of certain drugs that take place in the proximal tubule. You have a lot of reabsorption of sodium, a lot of reabsorption of water, and this is the only place where you reabsorb things like glucose and fructose and amino acids. So a lot of things take place in that proximal tubule. Now, again, I want to remind you that the osmolarity of the tubular fluid here is going to be the same as what you have over here in the blood, and it's about 300 milliosmoles per liter. So it's isosmotic to your blood. Okay, just keep that in mind, because this is so freely permeable to water. Water always wants to move across the membrane until it reaches osmotic equilibrium. So it's going to be the same. Okay, so that's going to be important at a later date. So this is the end of the proximal tubule.